All right, I'm online, so live streaming has started, but it's not time for class yet, so I can answer some questions if anyone has any. So far, no questions. All right.
I have a quick question.
Yeah.
Um, are you going to be opening up any more assignments before the final or no?
That is a good question.
Because I noticed we didn't do like I know you gave an ungraded application of Dijkstra's
Mm-hmm.
and the family one. I noticed we're like skipping those kind of.
Yeah, because there's not enough time to do all of them. One is ungraded. I gave you guys the ungraded A star and A star versus Dijkstra's algorithm. So that one is actually longer than the usual assignment because the usual assignment is just use one of the two algorithms, and this one uses both, which I think is beneficial because that way you can actually compare and contrast the two approaches and see how they are different. Um,
Mhm.
yeah, so the family one, okay, I can assign it and make it due maybe on the day of the final exam, so that can potentially be something I can do. Um,
If it's gonna relate, I meant more as like a forms of practice also because usually the assignments are a big help for preparing for the test and stuff.
mhm. Yeah, the scope of the exam is, yet another question, because this is the first time that I have to do final exams, fully remote and online. So there's that consideration too. Exam 2 is a good, dry run, but at the same time, it also taught me certain things that I did not expect. um, so yeah, so uh, I'll think about it. I need a little bit more time to kind of think about all that stuff.
All right.
Yeah, but thank you for the suggestion. But I will give you guys, some practice. I think that's always going to be beneficial. Um,
Yeah.
yeah. So what we'll do today, we got about 10 more seconds before noon. So what we'll do today is we're gonna let me mute one of my tabs first. There we go. Okay, that's my Exchange tab. So what we'll do today is to go through the ungraded assignment. So even though it is marked ungraded, which means whether you do it or not has no direct grade impact. It's always a good idea to do it, just because it's just a good way to understand the algorithms. All right, so it is noontime. So what we'll do is we'll get started with that one first. So that one is, you can find it in the announcement, the problem itself or the question itself. So we go to announcements, go to the PDF, which basically shows you a graph, of what you would normally see. Okay, so the graph is right here. Okay, so I'm just showing you the graph here. And once again, the nice thing about uh, using this approach, teaching online, okay, remotely. Okay, I was looking for the words and it was difficult for me to find the words today. Um, is you can open this on the side, also, so this way I don't have to display this using live stream. So that saves up a little bit of space, on live streaming. So I can just focus on the trace. So I would put this one on the side, on your screen. So over here, and I would also open up the algorithm, choose one. Okay, they're on the same page anyway, so if you find one, you'll find the other one. So we'll go ahead and follow maybe Dijkstra's algorithm first. So in terms of graphs, go here and go to the algorithm. Okay, and you can either open the PDF or the HTML. It doesn't really matter which one. So I'm just going to open HTML and go to the Dijkstra's algorithm. And once again, I'm going to peel this off, from my browser. So this way it does not take up any screen space. So I hope you guys are doing about the same thing. Okay, so this way you can look at the graph on one side and then look at the algorithm on the other side. And so now I can focus on just the trace itself in the area where things are getting recorded. All right, so there we go. I'm just using a regular, spreadsheet program, as the, just a big gigantic table to keep track of everything. So I'm going to use the same approach as I did in previous classes. So we have to keep track of a few things in Dijkstra's algorithm. If you look at all the things that get changed, Q obviously is important because Q is the set of vertices where their L value just got changed. Okay, so whenever the L value of a vertex got changed in Dijkstra's algorithm, it means it can potentially impact the L value of some other vertices, and that's why it's important to keep track of vertices in Q. In the algorithm, V is a variable that focuses on just one particular vertex that we pull out of the set Q for consideration. So V is definitely important. There's also a W local variable because WV is an edge. Okay, so we are basically looking at all the vertices where they have a direct edge to go to vertex V, because those are the ones that can potentially be impacted by the L value change of vertex V. And then we got the L values itself. Okay, so L value is on the per vertex basis. We have 5 vertices in our case, so if you just kind of use one column per vertex, I think it's an easier way to kind of keep track of stuff, this way. But you can track it slightly differently if you want to. You can look at it as a set of 2 tuples, that will work as well. And then we have E prime, as a set to contain all the quote-unquote solution edges. So the solution edges, each one is basically an edge that is a part of a shortest path from one vertex to the destination. Okay. So when you look at the algorithm, okay, I think these are all the variables that we have to keep track. But when you look at the initialization, which is the third line down from the top, well, first of all, we have to identify a subset that are identified as destinations. And in this case, E is the only one. So it is written in the text that says E is the only destination. So that's our only destination. So that is the only vertex that has a 0 for its initial L value. All of the other ones has infinity as the initial L values, because the L value in Dijkstra's algorithm is representing the length of the shortest path from a vertex to a destination vertex. And since we have not explored the graph in any way, so everything is initialized to infinity. All right, so now we move on from that to the initialization of the set Q, which is basically just the set of all the destination vertices. In this case, only E is our destination vertex, so E is the only one in set Q to begin with. Now the interesting part about this Dijkstra's algorithm is it can keep track of multiple destinations. So if all destinations are considered equal, the algorithm will find the shortest path to a destination. So that's it's kind of really helpful in some cases. So that's our initialization. E prime is empty. Okay, that's our last initialization before we get into the loop. All right, so row 4 is representing when we got into the loop. Okay, what is our set Q? Q is non-empty, so we select a V from Q. So in this case, we don't really have to read the rest of that statement, the statement that says you select V in Q such that blah blah blah, because there are no other alternatives here. So we have to choose whatever is the only element in Q to be our V, but at the same time we have to make sure that Q does not have that element anymore. So that's how we get the whole thing initialized. And now we have to look into all the incoming edges to vertex E. So when you look at all the incoming edges into vertex E, we have BE, we have CE, and we also have DE. So it doesn't really matter in what order you explore those incoming edges to vertex E, as long as they're all considered, it's fine. Okay, so we'll look at vertex B first. So when we look at vertex B, the next thing we need to do, according to the algorithm, is to look at L of V plus D of E and see if it is L less than L of W. Okay, so I'm just trying to document here what we are looking at. So we want to look at L of V, and we add the distance of the edge E, which in this case is WV, that's the edge. And we want to see if that is less than L of W. In other words, we want to ask, did we just find a shorter path for W to get to a destination? That's basically what it's asking. So on this row, on row 5 of the trace, we are now looking at the sum of L of V, which is 0, plus the edge WV, which in the graph has a distance of 50. And we want to see if 50 is less than L of W. Since W is B and L of W is infinity, we are comparing 50, which is a non-infinity number, to infinity, and the answer is yes, it is less than. So now we have to first update the L value of B, so that it's now 50. And then we have to remove all the outgoing edges from vertex B, but since E prime is empty at this point, so there's nothing to remove. And then we add the edge WV to E prime. So now E prime has one single edge in it, which is BE as a single edge. And then since we just changed the L value of B, we are adding B to the set Q to remind ourselves and go like, maybe we need to look at all the incoming edges to B at some point. So now we're done with vertex B or BE as an edge. So now we look at CE as an edge. Basically, it boils down to the same thing. The current L value of C is infinity. So when you look at 0 plus 41, okay, in this case, which is just 41, it is less than infinity. So once again, we get into the then branch of the conditional statement. So L of C is now 41. We remove all the edges coming out of C from E prime, but since E prime does not have an edge of C comma something, so there's nothing to remove. And then we add the new edge, which is CE, into E prime, and then we add C into Q. So now Q, the set Q, has B and C in it. Then we look at the third edge going into vertex E, which is DE. So kind of the same deal, except this time DE has a L value of 20. After we get into the conditional statement, we determine that 20 is less than infinity. So D now has a new L value of 20. And once again, there are no outgoing edges from D in E prime. So E prime just got a little bit longer. Okay, so it has got BE, CE, and now also DE in it. And then we also have to remember to add D into the set Q, because the L value of D just got changed. So that concludes the inner for each loop, because we only got 3 incoming edges to vertex E. So now we get back to the outer loop, which looks at Q and ask, is it empty? Nope, it is not empty, so we cannot exit the loop yet. But this time when we select a vertex for V, we have to be careful, because the algorithm, the Dijkstra's algorithm is a greedy algorithm. It always looks as the most promising element. So in this case, it would be vertex D, because when you look at the L values for B, C, and D, vertex D has the lowest or the least L value. So D is going to be selected as our V, and we have to remember to remove it from the set Q. Oops, one extra comma over here. Let me get rid of that. There we go. All right, so now we have to look at all the incoming edges to vertex D. There's only one, okay? Only vertex A has an edge to vertex D. And once again, because vertex A currently has an L value of infinity, we know that we just found a shorter path from vertex A to a destination. And in this case, the L value is going to be the L value of D plus the distance of the edge AD. So the sum is going to be 40. So we update it to be 40 over here. We do not have any edges coming out of A in set E prime, so there's nothing to remove, but we do have to add this new edge into E prime. So it has got BE, CE, DE, and now also the edge AD in it, like so. And we have to remember to add vertex A into Q. So Q now has vertices A, B, and C. And because this is the only edge going into vertex D, we are done with the for each loop. So we go back to the while loop. The while loop looks at Q and it says, are you empty? No, I'm not empty. So that means we cannot exit the loop yet. So now out of vertices A, B, and C, we have to find the one that has the least value, which is vertex A. So vertex A is now our new V. And then we have to look at all the incoming edges to A. So interestingly, vertex A does have one incoming edge, which is vertex B. So we look at vertex, BA, and we ask, well, did we just find a shorter path for vertex B to get to a destination? Interestingly, yes. Okay, the answer is actually yes, because the length of the shortest path for B to get to a destination is 50. Okay, but we just found a shorter path because L of A is 40, but the distance of the edge going from B to A has a distance of 0. 0 plus 40 is still 40. 40 is less than 50, so we go into the then statement and then we update that. Okay, so the L value of B is now 40. And this time we got something to do because the edge BE should not be in the set anymore. Instead, we have an edge BA. Okay, so I'm combining two steps into one. I'm replacing BE with BA, and C is still here, DE is still here, AD is still here. All right, so let me see if there are any questions. Nope. Okay, I thought I saw some motion on the on Discord, but that was mistaken. Okay, so now we have to go to ABC. Oh, I forgot one thing. When I chose vertex A, I should have removed it from Q. So now we have to add B back into Q, but B is already in Q, so there's no change to Q at this point. Now we ask, do we have any other edges, incoming edges to vertex A? The answer is no. Okay, vertex A has 3 outgoing edges, but only 1 incoming edge, which is BA. So we are done with that. Now we go back to the main while loop and we ask, is Q empty at this point? Q is not empty yet. It has got vertex B, vertices, B and C in it. So between B and C, vertex B has the lower L value, so we choose B to be V at this point and remove it from the set Q. And now we have to look at all the incoming edges to B. It has got one incoming edge, which is vertex A. Okay, so we look at the edge AB, and then we ask, did we just find a shorter path for vertex A to get to the destination? And the answer is no, because vertex A already has an L value of 40, and if I use vertex B to get to a destination, so from A to B has a distance of 1, and then from B to one of the destinations has a length of 40, so that would be 41. 41 is not less than 40, so we do not update anything in this case because the then statement of the conditional statement does not execute. So do we have any questions about this? Was anyone confused by the quote-unquote loop between A and B and somehow ended up with an infinite loop in the trace? hope not. Okay, so I'm not seeing anyone typing anything, so I'm guessing everybody got this one squared away. Good. All right. So now we go back to the outer loop. Okay, question?
Oh, never mind. I misheard you. I thought you were about to say this was it. It was done. But
Oh
keep
no, not
going.
not yet. Yeah, not yet. So we go back to the while loop. The while loop looks at the set queue and asks, "Are you empty?" And the queue says, "No, I'm not empty. I still have one vertex left, which is vertex C." So now we have to take vertex C out of queue into local variable v, and queue is now empty. So now we have to look at all the incoming edges to C. So vertex C has got two incoming edges. It has got incoming edge B, and it also has incoming edge A. So we look at B first, okay? So the question is, did we just find a shorter path from vertex B through vertex C to a destination? The answer is no, because if you look at the L value of C, it is 41. And if you add the distance of B to C, which is 2, then it is 43. And 43 is not less than 41, so the then statement does not execute, so nothing got updated. So now we move on to the edge AC, and we ask, well, are we finding a shorter path from A to a destination through C? And the answer is no, because L of C is 41, and the distance from A to C is 3. Now, I know that is not the shortest distance. Actually, it is the same as the other one because you can go through B to C too, but it doesn't matter because when A goes through C to E, that path has a length of 44, which is not less than what L of A currently is, which is 40. So we are not going to add anything. And when we get back to the while loop, we look at the set queue, and set queue is now empty. So we are done with the algorithm at this point. So do we have any questions about this trace? No questions? All right. So I can certainly, save the spreadsheet and upload it at the end of the lecture. So this way, you kind of have a permanent copy of what I worked on today. And I will even update, the name of the sheet so that it reflects what this one is about. So this one is Dijkstra's algorithm. And now we can move on to the A-star algorithm. So before I move on to the A-star algorithm, are there any questions about Dijkstra's algorithm? All right. So if you don't have an immediate question, it's okay. If you compare my trace with your own and you find that they are different in some way and you cannot explain why they are different, you can certainly send your trace to me and we can talk about how they are different and which step might have caused the differences. Okay, so do we have any questions at this point?
None from me, at least.
Okay, excellent. Thank you. Anyone else? Nope. Okay. So once again, if you do have a question and but later on, that's fine. You just go ahead and you either direct message me or use the general text channel of the class.
Actually, I have one question.
Yeah, go ahead.
So when I did this algorithm, I completely forgot that Dijkstra always chooses the closest one, right?
Correct. So yeah. Go ahead.
If you don't do that, like when I just went in complete order, like it was a queue, so just always took the front one.
Okay.
And it still worked. Is that coincidence, or because I still got the exact same E prime, and the algorithm finished faster.
Let me think about that.
Okay.
So if you're not using the greedy approach and the vertex has multiple paths to a destination, then it is possible that you can find a not so short path first, Okay, so the initial path that you choose would not be the shortest one. So then later on you will find a shorter one, because everything in vertex in Q has to be examined. Okay, we have to look at every
Yeah.
single thing in Q to begin with. So that means it will correct itself later on to find that shorter path. But that means you would put that vertex back into Q because its own L value just got changed. So you would put the vertex back into Q, and that can potentially impact other vertices that get into that the original vertex that got removed from Q. So I'm just trying to think of a case where it would not find the solution.
Yeah.
I cannot think of one right now, but I don't have a solid proof that it will find the shortest path either. Okay, so so this one needs a little bit more time, and I'm gonna need some off class time to think about it, to basically
Okay.
to prove it one way or another, because I can either prove that if you do not use this clause over here, if you don't find the one that has the least L value, either I find a counter example where the algorithm does not find the shortest path, or I can do a proof to show that the algorithm will find the shortest path, but you might end up re-exploring the same vertex multiple times, which makes it less efficient.
Okay. That
Yeah,
makes sense.
yeah, but
Uh,
I don't have an offhand answer right now, because I think this one requires a little bit more thoughts into it.
okay. I'll just send you like a picture of it with a little message for a reminder.
Okay, all right, sounds good. All right, so without any further questions, and I'm reading the text channel. Okay, so without any further questions, we're going to move on to the A star algorithm. So once again, if you kind of doing the whole thing with me, go scroll the module 0310, which is the graph discussion. Just scroll down a little bit to the A star algorithm, and I will start a new tab over here to log the trace of the A star algorithm. So the A star algorithm works quite differently compared to Dijkstra's algorithm, and yet there are some similarities. The stuff that we need to track down here is a little bit more than the other one. We need to track the set O, which kind of serves the purpose of Q. Okay, so just different names. One goes from the start to the end, and the other one goes from destination back to all the other vertices. And then for each iteration, we choose a vertex, and the variable name is C in this case. And then C goes to a particular neighbor, which is N. And there's a local variable T, just for comparison purposes. And then we have we have three things to track in this case. The first one is function G, and function G is the known shortest path from the start vertex to a particular vertex. So it's the actual shortest the length of the shortest path of going from the start vertex, which is vertex A in this problem, to a particular vertex. So we got A, B, C, D, E under G. So obviously we need to kind of be more careful with spacing here, because we don't have a whole lot of space if we're not careful. So function function f on the other hand is an estimate. Okay, it's an estimate of the shortest path, the length of the shortest path from the start vertex through a particular vertex to the destination. So once again we have A, B, C, D, F, A, B, C, D, E over here, and we'll go ahead and try to save some space here. And then we have previous, and the previous is just for tracking, so that we can backtrack from the destination vertex all the way back to the start vertex. So but looking at it as a function, it also has A, B, C, D, E as the domain. Okay, so there we go. All right, so we'll combine these five. combine these 5 just so that it's easier to visually see, what is what. And we can even highlight a whole bunch of columns the same color. Not sure whether it was helpful to you guys or not, having different colors for different columns, but I think it helps a little bit in terms of identifying what that column is for. Okay, so now we can go ahead and start to do some initializations. So according to the initialization, the G value of just about everybody is infinity because we have not explored anything except for the destination itself. So G of E in this case is going to be 0 because the length of the shortest path from the destination vertex to itself is 0. It's already there. But everybody else is going to have infinity. Okay, I'm just using letter I for infinity here. F value is the same thing because it's really just an estimate of the shortest path going through a particular vertex to the destination. So only the destination vertex has an F value of 0. And then for the previous function, everybody has undefined. Okay, because even E itself has an undefined previous because we are not trying to form a loop from E to E. Because if we are already at the destination vertex, it does not need a previous. Okay. All right. So that's the initialization for G, F, and previous. And then for O, the initialization is quite simply the start vertex. So the start vertex in this case is vertex A. So this is the initial condition. If you look at row 3, this is how we got the whole algorithm started. Okay, what just happened to here? There we go. Okay, so row 3 is representing the start condition of the entire algorithm. So now we can go to the while statement. Okay, so the while statement is not simple like Dijkstra's algorithm anymore, because in Dijkstra's algorithm, all we need to do is to say, well, is Q empty or not? Okay, but this one is a little bit more complex because this one is asking, is any one of the element in O, does it have a F value that is less than G of X, which is the destination? So the only vertex in this case is F of 0. Oh, okay, I take it back. I just totally messed up here. And nobody noticed or nobody mentioned anything. It's the exact opposite. Okay, we do not start with the end here, we start with the beginning. So vertex A is the one that got the G value initialized to 0 because it is the start vertex. So the start vertex has a length, the length of the shortest path from the start vertex to the start vertex itself is 0 because it's there already. But then we have to look at the F value, which is the G value plus the heuristic from vertex A to vertex E. And according to the assumption, that is just 5. 0 plus 5 is 5. Okay, now it makes more sense because otherwise the algorithm would not go into the while loop at all. Okay, so I apologize for not initializing G and F correctly because I was still in the mindset of Dijkstra's algorithm. Okay, so now when we look at the condition of the while loop, we're asking, does any one of the vertices in O, does anyone have a F value that is less than G of X? G of X is G of E, which is infinity. But when you look at the F value of A, it is 5. 5 is less than infinity is true. So we can go into the while loop. Okay, so this is really important because Dijkstra's algorithm has a much simpler way of determining whether we should continue the while loop or not. And then A star has a kind of more difficult way to evaluate that. So once we get into the while loop, we ask, okay, so which one of the vertices has the least F value? Well, since we only got one vertex in this case, it's got to be vertex A. So now we remove vertex A from O. Now we have to look at all the outgoing neighbors or all the outgoing edges of vertex A. Vertex A has got 3 outgoing edges, AB, AC, and AD. Okay, so we'll focus on one at a time. So we look at the outgoing edge AB. So if we go from A to B, T which is really just the sum of g of c plus d of cn, is just 1. And then we ask, is t less than g of n? So g of b at this point is infinity right here, and 1 is certainly less than infinity, so we have to we go into the then branch of the conditional statement. So b has, okay, I think Kevin's mic, okay, was on. Okay, so b now has a new g value. Okay, so because we get into the conditional statement, so according to the algorithm, the first thing we do is we add vertex b to O. So now b is now in O, and then we update the previous of b so that it is now A instead of undefined. Then we update the g value, which is 0 plus 1, which is just 1 at this point. And we also have to update the f value of b, which is 1 plus the heuristic from b to e. So the heuristic from b to e is just 1, so we got 1 plus 1, which is 2. So do we have any questions about row 5? When we consider the edge AB, this is what happens. No questions? All right. So now we consider the edge AC. So when we look at the edge AC, C has a distance through A from the start vertex of 3, because it's 0 plus 3. So we ask the question, is 3 less than the g value of C at this point? The g value of C at this point is infinity. 3 is less than infinity is definitely true. So the first thing we do is we add C to the set O. So the set O now has B and C in it. And then we update the previous vertex C so that it is also A. And then we update the G value, which is now 3. And then we update the F value, which is 3 plus the heuristic from C to E. So that's 10, so that means the sum is 13. All right. Now we look at the edge AD. So the edge AD has a distance of 20. So 20 plus 0 means t is now 20. 20 is less than infinity is true. So we go into the then statement. So we have to remember to add D to the set. So the set O now has B, C, and D in it. Then we update the previous of D so that that is also going to be A. And then we update the G value, so that it is 20. Then we update the F value, so it's 20 as well. It's 20 plus the heuristic from C to E. The heuristic from C to E is 10. 20 plus 10 is 30. So we put a 30 here. Nope, okay, I take it back. We're looking at DE. So the heuristic from D to E is 20. So 20 plus 20 is 40. There we go. All right. So are we okay up to this point? Do we have any questions? No questions? All right. So that concludes the inner loop, the for each loop. Now we have to go back out to the while loop. So once again, when we look at the while loop, we have to look at the f values of all the elements in O, and then we ask, does at least one of these have a f value that is less than g of e? G of e is still infinity. It has not been updated since the initialization. But when you look at the g value of B, C, and D, they are all non-infinity, which means all of them would fit the requirement of being less than g of e. So we certainly are not quite done yet in terms of the while loop. So now we get into the while loop, and then we ask which one of B, C, or D has the least f value. In other words, we are looking at the elements in O, and then we ask which one is the most promising. Okay, and right now vertex B looks the most promising because it has an f value of 2. And we have to kind of remember what the f value is representing. The f value is representing the length, the estimated length of the shortest path from the start vertex through vertex B in this case to the destination. And it's only 2 compared to 13 and 40. So certainly B looks like the most promising vertex to explore. So we choose vertex B to be the local variable C. And now we have to look at all and remove it from O. So O now only has C and D in it. C comma D. There we go. So now we have to look at all the outgoing edges of B, which has A and also C. Okay. And also E. So there are 3 outgoing edges from B, A, C, and E. Let me double check. A, C, and E. That's correct. So we look at BA first. So when you look at BA, we are asking, have we just found a shorter path to get to vertex A from A? This path, which is from A to B back to A, has a length of 1, as opposed to G of A, which is 0. So we haven't found a shorter path, so there's nothing to do because we are not getting into the then branch. But we do want to update T here because T is the sum of G of C, which is G of B, plus the distance of BA, which is 1. So 0 plus 1 is 1. But it doesn't really do anything because G of A is already a 0. Okay, so we cannot go lower than that. Now we look at BC. When we look at BC, we ask, what is the T value? So that is G of B, which is 1, plus the distance of the edge, which is 2. 1 plus 2 is 3. And then we ask, well, did we just find a shorter path from the start vertex A through vertex B to vertex C? The answer is no, because G of C is 3 already, and T is actually 3 in this case, so we haven't really found a shorter path. So we got to move on to BE. So when we look at BE, it's kind of the same deal. Okay, we first have to figure out the T value. So the T value is going to be 1, which is the shortest path known at this point to vertex B from the start vertex, to, plus the edge distance of the edge BE, which is 50. 1 plus 50 is 51, and then we compare 51 to the current G value of E at this point, which is infinity right here. And 51 is less than infinity is true, so we get into the then branch, which means the first thing we do is we add vertex E to O. So now we have C, D, and E in it. And then we update, the first thing we update is the previous. So the previous of E is now B. And then we update G first. So the G value of E is now 51. And the F value of E is also going to be 51 because the heuristic to go from E to E is 0. So now we do all this update. And now we have just concluded the for each loop in the algorithm because we have looked at all the outgoing edges of vertex B at this point. So do we have any questions about this step of the algorithm? Okay, I'm not seeing any questions. All right.
Sounds good to me.
All right, cool. All right, so we are going back to the beginning of the while loop, in which case we are looking at all the vertices C, D, and E, and then we ask, does any one of these vertices have a F value that is less than G of E? So this time it is a little bit interesting because G of E is no longer infinity, it is 51. So now we have to ask, do we have at least one of these F value, okay, F of C, F of D, or F of E, being less than 51? And the answer is yes, okay, because both C and D have their F values being 13 and 40, which are both less than 51, so we do not terminate the while loop yet. Then we get into the while loop, and then we have to ask, between C, D, and E, which one looks the most promising? C certainly looks the most promising, so we pick C this time. So remember this cell C is reflecting vertex C, and the column heading C is the variable C, so they are different. Okay, so vertex C has outgoing edges, but it only has one single outgoing edge, which is from C to E. So we have to look at that particular edge. So now we have to say, what is the sum of G of C, which is 3, plus the distance of the edge CE, which is 41. So 3 plus 41 is 44, and then we have to ask, did we just find a shorter path to vertex E? And the answer is, yep, we did. Okay, because the current G value of E is 51, and we just found a shorter path going from the start vertex A to C, then to the destination vertex E. So we have to go into the then branch. So when we get into the then branch, we have to add vertex C into the set, which, oh, I forgot about this. I forgot to remove it earlier. And we have to add E, not C, into the set. But E is already in the set, okay? So it doesn't really change the set O, because adding E to a set that already has E in it doesn't really change the set, okay? Then we have to update the previous. So the previous of E is no longer vertex B, it's going to be vertex C now. Then we have to change the G value. It is no longer 51, it is now 44. And we also have to now change the F value. It is also not 51, but 44 now. Do we have any questions? No questions? All right. So if there are no questions, then we move on, because this is the only iteration of the for each loop, because C only has one outgoing edge. So now we have to go back to the while loop, which is now asking, does any one of these two vertices in O have a F value that is less than G of X? So G of X, G of E has a value of 44. F of D has a value of 40. 40 is less than 44, so at least one of the two elements has an F value that is less than G of E, so we have to get into the loop again. Okay, we have to perform another iteration. So now we have to choose of the two, D and E, which one should we choose? Well, one has an estimated shortest path of 40, and one has the length of the shortest path is 44. So we're going to choose the one that is the most promising, which is vertex D. And as soon as we choose it, we have to remove it from the set O. And now we have to look at all the outgoing edges of D, which is only got one, which is DE. So now we have to compute T, which is G of D plus the distance of the edge DE. G of D is 20, and then the distance of the edge from D to E is also 20. 20 plus 20 is 40. So we have to look at 40 and compare that to G of E. G of E is 44. 40 is less than 44, so that means we have to go into the then branch again. So this time when we get into the then branch, we add E to the set O again, but it's already in it, so there's nothing visible here, no visible changes to O. Then we have to update the previous again, so that it goes from C to D, and then we update the G value of E to 40, and then we update the F value of E to also 40, and that concludes the for each loop. Now we have to go back to the main loop, and then we ask, okay, of all the elements in the set O, does any one of those have a F value that is less than G of E? G of E is 40, and the F value of E is also 40. 40 is less than 40 is false. So we do not have any elements in O that looks promising anymore, and that concludes the execution of the algorithm. It ends with one single element left in O, and that concludes it. So do we have any questions about the execution of the A* algorithm in this case? I'll go ahead and give you guys a little bit of time to think about this or ask questions when I save the file so that we have this thing for you guys to review later. All right, so any questions? No questions. Let me check the output of the A star algorithm against the output of a program that I have written, and they are consistent, so I didn't make any mistake here. Okay, very good.
Can you
Mm-hmm.
express the answer?
Can I express the answer?
Yeah.
Uh, what do you mean? The
So what like the algorithm actually gives out is
so what the algorithm would end up doing is it would use the previous, starting with the destination E. So it would basically, it would know to get to E, I have to get to D first. But then to get to D, I have to get to A first. And then A is the start vertex, so it doesn't have a previous. So this is how I can figure out the shortest path from vertex A to vertex E, is to start with vertex E and then track my way backwards using the previous. Does that kind of answer the question?
Can you say that one more time? I'm kind of getting hung up on just that part a little.
Okay, so when you look at the solution really has to do with previous. So we start with the destination vertex, which is vertex E, this guy over here.
Mm-hmm.
And let me use a highlighter. So we start with the destination vertex, which is vertex E, and then we ask, how do we get to vertex E? Now, according to the previous function, the previous of E is vertex D, so we follow that backwards, and then we figure out that, okay, to get to E, we have to go from D first. So that means we know that this edge is part of the shortest path from the start vertex. But then the next question is, well, we have to get to D. How do we get to D? So we look up the previous of D. It is vertex A. So now we know to get to D, we go from vertex A. Okay.
Mm-hmm.
But then we have to ask, how do we get to A? But we look at A, it has an undefined previous vertex because A is a start vertex to begin with.
Yeah.
So that's how we can figure out the actual shortest path from a single start vertex to a single destination vertex.
Okay, I'm seeing it. And then so basically this is basically what Dijkstra gives out too, because you can read it as from starting here, this is the path you have to take.
Correct. Yeah.
Okay.
Now, Dijkstra's algorithm is interesting because the solution of Dijkstra's algorithm is not a single path. So let me illustrate what I mean by that. Dijkstra's algorithm gives you E prime. Okay.
Yeah.
So when you look at E prime, it is not a single path. Okay. So when you look at E prime, which I'll highlight using a different color, it has BA, right? So it has BA, which is this path here. Okay, excuse me because I'm using my mouse. I didn't set up the tablet to do it. So you have CE. Okay, so you got CE. Okay, there we go.
Mm-hmm.
We got DE, right? So you got DE over here. And then we got AD, which is the kind of what we have highlighted. But so this arc or this edge is double highlighted. But when you look at the green portion, that is representing edges on a shortest path from any vertex to a destination vertex. So if you just look at vertex B, for instance, okay, if you look at vertex B and you ask, how do I get here to a destination vertex, using the shortest path? So if you start with vertex B, then you go like, well, the solution E prime only has one edge coming out of B, right? So you got to follow that one. So B has to go to C first, go to A first, A goes to D, and then D goes to E, which doesn't seem to make sense because, wow, I mean, we could have gone from B to E directly, but that edge is very costly. It has a distance of 50. But when you look at the length of the path from B to A to D and then to E, it is only 40, right? So that's the really cool part of Dijkstra's algorithm is it simultaneously solves the shortest path from every vertex to a destination vertex.
Isn't this one doing that too?
You mean the A star?
Well, yeah.
Nope.
Isn't it?
Nope, A star
Uh,
doesn't quite do it. So if you look
well,
at the output of A star, it keeps
yeah,
track of only one previous, right? So
yeah.
if one vertex can only have one previous, can only remember how to get there, it doesn't always necessarily give you the same solution. So in this case, it only solves, it only finds it only guarantees to find the shortest path from A to E. So if you ask, how do I get from B to E? What is the shortest path? You can see that to get to B you use A, right? And then from B, where do we go?
Mm,
We don't know. It doesn't track that, right?
I see what you're saying there. Okay.
Yeah. So now the question, okay, the $1 million question is, why do we have A star when Dijkstra's algorithm seems to solve all the same problems, right? Plus a little bit more because it gives you, the shortest path from every single vertex to a destination, and you can handle multiple destinations at the same time. So now the question is, why do we use A star if when there's Dijkstra's algorithm already? Well, the answer is Dijkstra's algorithm. Okay, let me give you an example. So let's just say that you're trying to. It depends on the application. If you're trying to find the quickest way to go from Sacramento to San Francisco, for instance, okay, do you care what is the shortest path from, I don't know, Los Angeles to San Francisco? Is that relevant to you? No, right? That's not relevant. And the most important part is, if you run Dijkstra's algorithm, it's going to take a lot longer, compared to the A star algorithm, if you really just want to know the shortest path from one single vertex to another vertex. Okay?
Yeah, because A star only maps one vertex to another.
And it makes use of heuristics. So the beauty of the A star algorithm is it makes use of heuristics. Now, the heuristics of the problem that I gave you guys, okay, let me just kind of show the whole thing, is awful. This is as bad as it can get. because this particular heuristic function is designed to make it to try to fool the A star algorithm to re-explore something over and over again. You can see that we have to update the shortest path to E 3 times. Okay, so yes, so you can come up with a heuristic function that is admissible, which means it will work. Okay, it guarantees that the A star algorithm will still find the shortest path, but it will trick the A star algorithm to go on a wild goose chase before it finds the shortest path. It will find the shortest path, so the algorithm is still correct, but it is no longer quote unquote efficient. Okay, but this one is by design like that, so that I can give you guys an example where the destination will be visited multiple times. But in reality, if you can find a functional and useful heuristic, then it helps a lot. Okay, so in terms of mapping, in terms of planning a trip, going from say Sacramento to San Francisco, a very easy to compute heuristic is really just the straight line distance as your heuristic. Okay, so what you do is you just say, if I draw a straight line from Sacramento to San Francisco, what is the distance of that line? Okay, you go like say 90 miles. Okay, so that is guaranteed to be not an overestimate of the actual driving distance, right? Because even if there is a path, okay, a highway that goes from Sacramento to San Francisco as a straight line, the distance of that particular road or highway would still be the same as your heuristic function. It cannot be shorter. Does that make
So
sense? Yeah.
yeah, so I really need to do when thinking of the heuristics is be confident that the heuristics I'm making are shorter than the actual distances.
Shorter or equal to. It can equal to, it just cannot be more than.
So, but you don't have to actually do any measurements. Like, so if I wanted to just say, I want to go from Sacramento to Los Angeles with one stop in Fresno, and I was just like, oh, it's 400 miles, or we'll just say it's 100 miles between here and Fresno and 100 between Fresno and there, which is obviously way shorter. Without doing any kind of measurements, you could actually use that like in
Yep.
that fashion.
Correct. So it will basically prune. Okay. The A star algorithm will start from the start vertex and expand it, right? So
Yeah.
because okay, so let's just say that you have on your map, okay, you do have one hop or one edge from Sacramento to say Roseville, okay, one hop to Eureka, okay, one hop to San Francisco, one hop to Stockton, okay. So when you look at all those hops, okay, which are direct edges from Sacramento, it will still explore, okay, Tahoe. It will still explore San Francisco. It will still explore Eureka, okay, but it is not likely to expand any further from Tahoe, from San Francisco, from Eureka, because um, the heuristic function going from Stockton to Los Angeles added to the actual distance of the edge from Sacramento to Stockton is going to be smaller compared to the heuristic plus actual edge from the other three unlikely pathways. Does it make sense?
Yeah, so the heuristics just help to make it so you don't have to explore everything.
Right. It's called a heuristic because it's based on the rule of thumb and estimate. It's not going to be always right. Okay, but it will give you an idea. It's a guidance kind of thing, right? So it basically guides the A star algorithm to if the heuristic function works the way it's supposed to, then it is one, really quick to compute, and two, it will guide the A star algorithm to expand fewer and fewer vertices. So in the ideal case, you end up with a lot of vertices still in the set O, because the heuristic function is realistic and accurate enough to say that none of these can actually be shorter than what I have already.
Oh, so you ideally want to have it close to accurate heuristic function.
Correct. Yes. Yeah. Ideally speaking, you want it to be as close as possible to the actual length of the shortest path, but it cannot be the actual length of the shortest path, because if you know that already, then you don't need to you don't need to go through the algorithm to explore. Does that make sense?
Yeah, then you could just trace the shortest path.
Well, not so much just to trace the shortest path, but if your heuristic function is the actual length to the destination, then you're not going to expand a lot of vertices along the path. You still have to expand some, okay, but not a whole lot.
Okay.
Yep. So the usual application in a usual application, the heuristic is going to be somewhere between 0 and the actual length of the shortest path. Okay, but that's just general, right? So if you plug in a 0 for all the heuristic values, then you just end up with breadth first search. Okay, you basically your heuristic function is not giving you any information to make good decisions. Now, will it still find the shortest path? Yes. Okay, but it's no faster than a breadth first search algorithm. Does it make sense?
Yeah, definitely.
Yeah, a breadth first search, breadth first search algorithm simply draws bigger and bigger and bigger circles from the point of origin, and it tries to touch the destination, and the moment it touches the destination, it's done. Okay, but if your heuristic function is uninformed, which means it is 0 for every single vertex, then it is not going to give you any actual help. Then A star algorithm de-evolves into breadth first search, when the heuristic function is 0. When the heuristic function is the actual length of the shortest path, then the A-star algorithm becomes a linear search, because it just kind of needs to follow the next one, up, then the next one, then the next one, then the next one. But the number of vertices that it would touch is a little bit more than just everything along the path, but it is going to be a very small number nonetheless.
Okay. And then I saw someone ask this in the chat. I'm sure that
Okay.
you would, like in a test, you would give us the heuristics.
That is a very good question. So let me read the text here. Carol asks, so what does the A-star algorithm tell us? What is the output? So I think we answered the question. Okay, very good. And then Brenda asks for the final if we have an A-star algorithm. Yes. So it depends on the format of the question. Okay, so I can potentially give you a graph with the cost, with the distances of the edges and the configuration, the topology of the graph, and then I will have specific requirement and go like, if I want to trick the A-star algorithm to revisit this vertex multiple times, okay, to update the G value of this vertex multiple times, how can you arrange the heuristic values to make that happen? So that is a possible kind of question for the final exam. So it is not necessarily that I give you all the values and you just kind of follow the algorithm. It can be me asking you guys how to configure the heuristic value in the case of the A-star algorithm, so that when the algorithm does run, it's gonna update the G value of some vertex multiple times. So it can be in that format. All right. Are there any questions, other questions about the A-star or Dijkstra's algorithm? Okay, apparently not. All right, so what I'll do is I'm gonna save the spreadsheet right now and upload it before I forget. So there we go. And Carol is asking, how much faster is A-star? That's a very tricky question, because it all depends on the heuristic function. If you have a really good heuristic function, it can be a whole lot faster. If not, it can be a whole lot slower. So let me pin this first. There we go. There we go. All right. So any other questions about Dijkstra's or A-star algorithm? James has a question. Okay, what is the big O of A-star? That is an interesting question. So the A-star algorithm does... Oh, okay, all right. So the A-star algorithm can potentially explore a vertex. So the question is, does it re-explore edges? Okay, so that's one of the interesting questions. Is even though in the A-star algorithm, okay, so when you look at the trace that we have right now, you can see how vertex E got updated 3 times. Okay, we got updated. Okay, my mouse pointer is moving because my cat is sitting on my other mouse. And my cat was also playing the piano a little bit earlier, if you heard that. Okay, so you can see that oh, I think this one is supposed to be here. So B goes here. Okay, remove that. There we go. So you can see how vertex E got its previous F value, G value, updated 3 times. Yes, that is a very skilled cat. But you can see how it's updated 3 times. So the vertex E was touched 3 times in the algorithm. But when you look at the edges, okay, have we looked at the same edge twice? Okay, And the way we can find out whether an edge has been visited more than once is we got AB, that's edge AB, edge AC, edge AD, BA, BC, BE, CE, and DE. We never revisit the same edge twice. Okay, so now the question is, can we make from this observation, okay, can we generalize and claim that the A star algorithm, assuming the heuristic function is admissible, which means it doesn't overestimate, and distances of edges can never go below 0, okay? So assuming that we can make all of those assumptions, can we claim, okay, that an edge will never get explored twice in the A star algorithm? Okay, now that's one question by itself. Okay, can we make that claim? The second question now is, if we do make that claim, okay, can we prove it? Okay, so when we ask the question, can we prove it, there are two ways to look at this. One is to say, Tech is probably wrong. I'm going to find a counter example to prove him wrong. So in that case, what you need to do is to come up with a configuration of a graph with a heuristic function that meets all the basic requirements. Okay, no overestimating heuristics, no negative distances, and so on and so forth. And yet, okay, when you run the A star algorithm, a particular edge get visited more than once. Okay, that's possible. So that would prove me wrong. On the other hand, if you want to prove me right, then you have to formulate a proof to prove that I'm right. Okay. Now these are fairly advanced topics. Typically, they talk about these in a class called Analysis of Algorithms. So you can kind of look forward to those classes when you move on to a 4-year university as an upper division class. But if you look up Wikipedia on the A star algorithm, it does tell you that the complexity or the worst case scenario of A star is the cardinality of E, because it can only go through, how should I put it? In the worst case, it will visit each edge exactly once, and that's it. So that's kind of one of the properties of the A star algorithm is, in the worst case, it will basically explore each edge at exactly once. Now, when you look at Dijkstra's algorithm, okay, Dijkstra's algorithm has a different time complexity because it does solve a slightly different problem. But we can also see in the trace for Dijkstra's algorithm that it does not revisit the same edge twice, okay? Because the edges are WV in this case, so it's edge BE, CE, DE, and then AD, BA, AD, and then we have BC and AC. So you can see none of the edges got explored or touched twice. So any questions about that? Yeah, the time code. Yeah, go ahead.
I just have one question, kind of about Dijkstra that I've been noticing when we run the spreadsheet.
Uh-huh.
Your algorithm you say is to find the fastest route from any vertex to a set of destinations, right? Not to just a single destination.
Correct. So it considers all destination vertices basically equal. So okay, so imagine that you're in Six Flags, right? This was the example that I used when I first introduced the algorithm. So if you imagine that you're in Six Flags with a young cousin of yours, and then the cousin says, I need to go to the bathroom. Okay, so yeah, that's the whole thing, right? So if you pre-solve that problem using Dijkstra's algorithm, as soon as you know which vertex you're on right now, the pre-solved graph, which consists of E prime, will immediately tell you which way you need to go to get to the closest bathroom from where you are.
Okay, I think I misunderstood it at first. I thought I was hearing it as you could think of it as like there's multiple people standing around, and each of them needs to find the closest to any bathroom near them. So multiple like destinations, and then the quickest path for those. But I guess you would just run the algorithm on each of those.
No, you just run the algorithm exactly once. So you basically pre-run Dijkstra's algorithm before the day you go to Six Flags. So after you run Dijkstra's algorithm, you no longer have a complete map of Six Flags, and instead you will only have the edges representing how to get to the closest bathroom from each point on the map. Do you see what I mean? So basically what you do, okay, if this is the scenario, is the day before you go to Six Flags, okay, you go online, you go to Six Flags website, you pre-download Six Flags theme park map, okay, and then you look at every single intersection as a vertex, and then you look at all the pathways between vertices as edges. Okay, so let's just say that the so-called distance is truly just the distance. Okay, there's no incline. There are no other considerations. So you now start to assign distances to all the edges. So what you do is you run Dijkstra's algorithm to pre-solve the entire map first. Now, after you run Dijkstra's algorithm, you end up with E prime, which is guaranteed to be a subset of E, right? Because we are only adding edges that we have considered into E prime, and so E prime has got to be a subset of E. So now, so it becomes a partial map of what you started off with. So you take that partial map or the solution map that you have with you to Six Flags. You keep it in your backpack. You don't need to use it for the most part. But the moment somebody asks, okay, I need to go to the bathroom. How do I get to the closest bathroom from here? Then you pull that map out of your pocket. Okay, you identify which vertex you're on right now. Okay, and then that map will only show you how to get to the bathroom that is closest to that point. Does that make sense?
Yeah, I see that. So
Yeah.
you can basically look at them if you're just standing in some random place in the park. You can be like, which vertex am I closest to, and then decide what the closest bathroom.
Exactly. So you can have so you can pre-solve that. You can pre-solve multiple maps, one for bathroom, one for water, one for food, and so on. So it doesn't matter what the emergency is, you just pull the right map out and you know exactly how to get to the closest something.
Okay.
Which is kind of cool. I mean,
yeah, that's
yeah,
really cool.
yeah. The A star algorithm does not do that, right? The A star algorithm means that you have to know, your start vertex, which is where you are, and then you have to kind of know where you need to go. Okay, if you have multiple bathrooms, okay, then with the current A star algorithm, the way it is structured right now, then you're gonna have to run one instance of the A star algorithm to each bathroom, and then you compare the length of the shortest paths, okay, to find out which one is the shortest. Then you can decide where you should go next. Does that make sense?
Yes.
So it's not quite as handy, in the same scenario where, I just need to go to one bathroom, okay? Which one is the closest to me? A star doesn't tell you that, okay? A star just tells you, if you tell me which bathroom you want to go to, I can tell you what is the length of that path. But if there are 20 bathrooms within the theme park, okay, then you're going to have to run A star on each bathroom with your current location as the start vertex. Then you have to compare the lengths of all of those shortest paths in order to decide which one is actually the shortest to you based on where you are.
Okay, I see that.
Yep. So they kind of solve a different type of problem. Now, there are probably ways to modify the A star algorithm to take care of multiple destinations. But that means, when you run the algorithm, the f value, and especially the f value, is not going to be computed the same way anymore. You basically will have to run. You have to look at the minimum of the heuristic values from a vertex to all of the destinations, and then take the minimum of all of those to factor into the calculation of the f value. So I think if you did that, then it will be it might find the shortest path to a destination, given that there are multiple destinations. I cannot say for sure because I haven't really tried that modification on the A star algorithm yet.
So the way Google Maps works
Mm-hmm.
basically then is it only you select one location from your place. It's kind of like A star in that sense of that it just finds the shortest.
Yes.
So you
So
can't just Panda Express and get
yes,
all the.
that is correct. Now, but an interesting modification of the Google Map or the Google navigation mechanism or algorithm is, I need to hit a Costco, I need to hit a Walmart, and I need to hit a Big Five. Okay, and I am starting from here. I need to get back to the same point. Okay, so give me the shortest tour. Okay, of visiting these three stores. So we know that, okay, there are multiple Big Fives in Sacramento, there are multiple Costco's, and there are multiple, Walmarts. So if you basically say, okay, let's assume all of these stores are the same. Okay, all Walmarts are the same, all Costco's are the same, and all Big Fives are the same. Give me the shortest tour so I can visit all three stores. Okay, now that is an interesting problem for Google's navigation, because that can potentially be useful, right? Because if you just say that, okay, I think all of these stores, all the Big Fives would have this item that I want, all of these Costco's would have the hot dog that I want, and all of these Walmarts also have this clothing that I want. Okay, so I just want to minimize my trip to get all of these items. So I can see how a modification of these algorithms can be useful, as far as Google is concerned. So this way, you don't have to plug in and say, if I go to this Walmart and then this Costco and then this Big Five, what is the total distance or the amount of time? Okay, and then you have to pick the other three, pick the other three, pick the other three, pick the other three, and we already know this is not going to be this is going to take a while because there are so many different combinations. Does that make sense?
Yeah, I was just gonna say that the issue with that is like there's so many side streets, like the computing time would be a lot longer.
Yep, and also in terms of Google search, the interesting part about Google navigation is, a well published or well used solution is not going to be the solution anymore. I'll give you an example. Okay, so let's just say that a lot of people want to go from point A to point B. Okay, and everybody wants the shortest path. There's an event. Okay, so that means what we consider as the quote unquote shortest path under normal condition is not going to be normal anymore. It's not going to be the shortest path anymore because everybody is using that path. So exactly, there will be traffic. Okay, and traffic is interesting because it's not linear. It's not like it's not one over the number of people traveling in that path. It's worse than that. Okay, the collision type of situation is not reciprocal. It's worse than that. Okay, so that means if Google search or Google navigation is to take into consideration how many people are trying to go from one place to another place, and it's a burst mode kind of thing, it needs to do load balancing. It needs to configure the routes or the recommended paths in a way so that the actual final throughput is maximized, but it cannot give the same suggestion to every single person. So that makes a very interesting question too, because this is all dynamic. It's not static.
Yeah,
So
that makes sense.
Yeah, so I'm just talking about topics that are related to A star and Dijkstra's algorithm, but not we are not going to integrate those considerations into A star or Dijkstra's algorithm. It's definitely not okay. Not doing that in the final exam. But for those of you who are interested in algorithms, that's kind of interesting stuff to think about. And especially if you can tell your potential employer that oh, this is the kind of stuff that I think about in my spare time. Hey, that might be worth something in an interview. And then Carol typed, he has been thinking about that for the future, that most cars follow some sort of algorithms to get the shortest path. I feel like cars will have to let each other know what their path is going to be. Yep, yep, exactly. So that way the system, as a whole, can coordinate so that we basically just make everybody, it takes less time for each person to get to the destination. But that sort of algorithm is dynamic because traffic conditions changes, car accidents happen, and so on and so forth. So I think there's a lot of interesting stuff that can be done
So
with these types.
would that mean that Google Maps is more accurate the higher the percentage?
You kind of broke up in the previous one. Go ahead and say again.
So like Google calculates all its traffic and stuff from I'm sure many different factors,
Yes, it
cars, and from the information they're getting from their apps. So
yes.
would you say that their algorithm is more accurate the more you're using Google Maps, another map
Um,
system?
well, even if you're not using Google Maps, Google can still track your position, right? So so not you don't need someone to be using Google navigation in order for Google to collect data of vehicle movements. So it's probably doing that already because Google actually knows traffic conditions, and I think that's probably a combination of what is reported, what the highway police, what the highway patrol has in the database, and also data that Google itself collects by people just running Android, and having the location turned on.
Okay, that makes
Yep.
sense.
Yeah, it's interesting in some other way too because you're looking at your privacy issues on one side, and at the
Yeah.
same time you're also looking at information that can actually be quite useful on the other hand. So lots of implications from that sort of stuff. All right. And then Bo said IIRC they have limited access to DOT, Department of Transportation camera systems. Oh, I didn't know that. That is interesting. And then Brenda is typing something. Um, yes, we will have the final exam review on Wednesday, which is going to be mostly focusing on these two algorithms, these two graph algorithms. So understanding the algorithms, very thoroughly is going to be very helpful. I haven't really quite decided whether to put in some topics in predicate calculus. And I think William was typing something a little bit earlier, so I'm going to wait a little bit. Yep. Our final is going to be on the originally scheduled date and time. I believe he is correct about it. I'm just going to do a quick search on the side here. Okay, I found that you can actually look up final exam ARC, and it finds it. Right here, the third link. There we go. And this is a daytime class next Monday. Well, let me look it up first. Okay, our start time. This is a Monday Wednesday class, and the start time is noon. So we are looking at this. So we are looking at 18th, which is 1 week from today, from 12:45 to 2:45 p.m. There we go. Excellent. Oh, before CISP 4:30, because I wasn't really sure what it was. 4:30 p.m. or what. Okay, so that's our final exam. You can kind of consider today's run through of the algorithm as part of the review for the final exam, because the final exam is going to be, quite focusing on stuff that is after the second exam. All right, cool. And there's a sad phase because it's right before 4:30, which starts at 3. So that means, if you're in both classes, that leaves you only 15 minutes between the two final exams. Yeah, that's kind of bad. In a way, it's kind of good because you can use this class to warm up the engine for the other class. All right, so that concludes the lecture today, and I'm waiting for Carol to finish typing before I drop out of the live stream. But the question is 4:30? Yep, freak out session. Is 4:30 also going to be kind of like conducted like this class, where they restrict it to a certain time, like the face-to-face version? Okay. And Brenda types, so maybe we shouldn't include the predicate calculus since we all have another final exam. Okay. Well, let me think about it. Okay. Maybe we can make the predicate calculus thing something you can turn in, kind of like a homework assignment that you can turn in, when you have time to do it. So that's potentially something we can do. And then Bo said 3 to 5, but he hasn't said if it's FaceTimed. Oh, okay, I see. All right. So we're going to keep our time slot for now, at least. And the predicate calculus stuff, I think it's probably a little bit more interesting if I make it, turn it into an assignment that spills over to the percentage of a final. So that way it is not part of the 20% of homework assignment. It is actually going to be part of the 40% of the final exam, but it's not going to be in real time. You just have, some time to work on it. So that's something I can look into. All right, cool. So we are out of time today. I'm going to drop out of live stream, but I'll stay on the text channel to see if you guys have anything to say. Okay, you're welcome. All right, so I'm going to stop live streaming now, and we'll talk again on Wednesday, which is going to be our last lecture.